exams now.
Can we discuss it with each other?
Yeah, that's fine too. If you want to work together with someone, that's fine. If you want to work by yourself, that's fine. But it's important that you start practicing exam questions, because the test is worth 10%, which is significant. You know, it will help you out towards the end. Yeah, 10%. And in my opinion, it's not, with a bit of study, it's not going to be too bad to get a high score in this, because everything we did in this semester is not too difficult compared to what other stuff we'll be doing in semester 2. Okay, so yep.
Thank you.
Please try to get as much of this 10% as you can, is my point. Yeah.
Do you know, our finals, right? Is it going to be based on the syllabus after semester 2?
No, it's everything, 1 and 2.
Okay.
Which is kind of good because, you know, in previous years it was only semester 2, but this year it'll be semester 1 and semester 2, which I said is kind of good because the semester 1 content is easier than semester 2. So in a way, the exam would be easier than in previous years, but you have more to prepare. But the extra is easier stuff. So I think on balance it's a better deal this way for you. Yes, you have more to revise, but there's more easy stuff that could be in the exam. So I think it's a good thing that way. Okay, so what we're going to have a look at, it's not too difficult, just like in the last year.
Another question, but when will you finish grading the coursework?
Well, first I have to start it.
Sure.
And then after I start it, I'll work on it for 2 weeks, and then it'll be finished.
So after Christmas?
Yes.
I mean after Christmas holidays?
After the holidays, yeah. I always try to make sure that the students have the results before their tests so they know where they are at. So there's a chance that I might have it done before the break. So the earliest you'd have the results will be Friday of next week. Yeah? Yes. Oh yeah, the answer to yesterday's question. Thank you for reminding me. So if you remember, yesterday we had the situation where we had both treatment A and treatment B being the better treatment, and which one was it? So did anybody think about it or work it out?
I thought about it and it made me.
And then you stopped talking about it, yeah.
I stopped about it.
Really?
Yeah.
Okay, what did people conclude then? Which one was the better one, A or B? So I think the first time we did it, which results did show up as better? B, was it? And then the second time we did the calculation, it was A. And when we were looking at B, we were looking at everybody in total. But then with the A, we looked at them separately as small and large kidney stones. So the situation is actually that the A1 is really the better one. But the question is, how come the B1 showed up as being better when we looked at everybody in total? Now, it's difficult to understand this one because we're talking about small and large kidney stones, but there's another example which is exactly the same as this, which might be a bit easier to understand. So, I believe it was Berkeley University a few years ago. Berkeley University was taken to court because it was claimed that they favoured male applicants in their application. So when you were to look at the approval rate, for example, if you had male and female, and you say, well, how many men got approved for the course? They might say, for example, 25% of applicants got approved or whatever. And then for females, how many of them got approved for the course? And you might say 23%. So if you were just looking at this, you'd say, oh, well, shouldn't they be the same? There must be some kind of gender bias here. And Berkeley's case was that there isn't a bias, because what they did then was they looked at each department individually. So you had computer science, medicine. I will just say A, B, C, D, E is the different apartments. So in the different departments, when you look at the admission rate, maybe for this department, it was 20% male and then 21% female, and then maybe here this could have been 12% male, but 13% female, etc. So now when you look at this, instead of males being slightly ahead of females, when you look at it department by department, you can see that females are slightly ahead of males. And this is exactly the same contradiction we had yesterday, where when we looked at small and large kidney stones, it was better for treatment which one did we say? Treatment A, but when we were looking at the total, it was better for treatment B. So the reason this is happening, and it's the same reason for what caused yesterday's problem, was here we don't see, but what's happening is more female applicants are applying for more difficult courses. So for example, what you can't see here with this admission rate is how many were male applicants and how many were female. So this course is quite difficult, low admission rate. Maybe 200 men applied here and 400 women applied. 400 women applied here. So although the percentage is higher, the women were doing better here because there were more women. In total, more women got rejection letters, but only because more of them were applying to something difficult. And those that did apply had a higher success rate. But when you look at the total, you don't see that. You just see lots of failed applicants here. So actually, there was no bias between male and female. The female candidates were applying for higher ranking courses. This is the same thing that's happening with the small and the large kidney stones. I think large kidney stones are more difficult to treat. And maybe because of this, it was skewing the numbers. This is a very difficult example, but I'm glad that we did it because I just wanted to make the point that it can be very, very important how you look at things. If possible, you should try to look at things on a more individual level rather than as a large group. Yeah, there's many, many, many more examples of this, but if you were interested and you wanted to read up more about it, you won't forget the name of it. Simpsons Paradox is what it's called. So if you wanted to read more about it and see more examples, you could Google that. Okay, so we'll continue then.
There's a thing called Simpsons Index.
Oh yeah, well there's a couple of things, and there's Simpsons integration rule and so on. This is the statistics Simpsons Paradox. Yeah? In bio, Simpsons Index?
Yeah.
Is it a bio thing?
Yeah, it's biodiversity.
Yeah.
Oh, I don't know if it's... Would it be a statistical measurement?
It's like, you have like not secret, sorry. You measure the amount of life forms in each part of
Oh,
the
okay.
And then you make like sigma something
Okay, so it's a diversity measure, like you said. It could be the same guy because this is a statistics topic as well. Okay, so we'll continue now with probability trees. So yesterday we saw that one way we can put data together for calculating probabilities is in a table, but another way we can put it together is in a tree, and we can put the same information in a tree or in a table. So for example, I think yesterday we were looking at men and women and smokers and non-smokers. Yes? So you can do something similar as well but put in tree form. It would look like this. You would have male, female, and then smokers, and then non-smokers, smokers, and then non-smokers. And what you do, well, a little bit of vocabulary, so you'd want to write these now. These here, yeah, what are they called? Fancier word than that. These are called nodes, and these are branches on the tree, yeah. And what you put on the branches is the probabilities. So for example, yeah, this could be 0.5 are male, 0.5 are female. And then what you say is, if they're male, maybe they've got a 75% chance of being smoker, 25 non-smoker, and maybe it's the other way around here, 25 here and 75 here. So this is called a probability tree. These are called the nodes. And then these ones here are called the branches. And you start here. And then you end up on this column. Okay, so if you just want to write that down, we'll have a look at some examples here.
Are we going to use this as an example? Are we going to continue?
No, I just did this one for vocabulary, but we'll use a different one for an example. I'm sure some people have seen these trees before, yeah? Yeah. So do you remember, if you've seen them before, how it works? Like if I asked you, for example, what is the probability that you'll get a male and a smoker? So male and a smoker.
0.5 and
0.5 times 0.75. So the way it works is you start here and you want male, so you go this way, and smoker, so you continue this way. And as you move along the branches, the probabilities get multiplied. So this is the first rule. And then the second rule is if you have an OR. So let's say something like we want probability, let's just say probability of getting a smoker. Now when you look at this, you have two choices. You can go this way, male and smoker, or you can go female and smoker. And notice, because I said the OR, that makes a plus here for this. So the way it works is we go male and smoker, which we have, or we can go female and smoker, and we'll have 0.5 times 0.25. And that's really the only two calculations that you would ever really need to do here. Some things to note. The probabilities on the branches always add up to 1 from each node. So for example, from the start node, we have this, and when they add together, we get 1. From the male node, we have this, and when they add together, we get 1. And from the female node, when we have this and this added together, we also get 1. So the probabilities add up to 1 from each node. But of course, if you add them all up, you won't get 1. You get much more than 1. So let's have a look at some examples. I think we'll do one that's a little bit more difficult. Can I scroll down? Do you have this? Yes? Yeah. Okay. Okay, so maybe I'll just draw the tree. Well, no, I'll go left to right. And then we'll put a node here and here. Then we'll put a node here and here. Here and here. Okay, so we could do something like you can have tea or coffee. Oh my goodness. You could have tea or coffee for breakfast, and then afterwards you can either have a pastry with it or not. So let's imagine people who have tea, they can have pastry or no pastry, and here we can have pastry and no pastry. Let's say this is 0.8 and this is 0.2. Let's say this is 0.2, this is 0.8, and let's say this is 0.9 and 0.1 then. Okay, I'll give you some easy ones to calculate first, and then we'll have some harder ones now. So, first one is probability of having tea and a pastry. Probability of, let's say coffee and a pastry. Probability of tea and no pastry. Probability of coffee and no pastry. And then we'll just have probability of pastry, and then one more easy one, probability of no pastry. Okay, I'll just give you a minute to try these. They won't take too long. Get my calculator too. Okay. What's the first one?
0.04.
0.04. And then coffee and pastry?
0.72.
0.72. Then tea and no pastry?
0.16.
1/6. Coffee and no pastry? 0.08, isn't
Yeah.
it? And then pastry?
0.6.
Now, yeah, what's it?
0.76.
0.76.
Yeah.
So you have to go tea and pastry, and then coffee and pastry then. And then last one, not pastry, 0.24. Now do you notice how, for example, here, if pastry is 76%, then of course not pastry will be 24%. The total here should make 1. Now if you didn't know that, I'll write it down here, but if you have A plus not A, the total has to be 1. Which makes sense if you think about it. If I'm saying, for example, 80% chance that it could happen, then it must be 20% chance that it can't happen, because the total has to make 100%. If these are the only two possibilities. Okay, let's have a look at something a little bit extra we could do here. So I'm going to put this in a table just to show you that it's just two different ways of looking at the same thing. So we can have tea and coffee, pastry and non-pastry. So the first one, tea and pastry, where's that now? 4%. Tea and no pastry, 16%. Coffee and pastry, 72%. Coffee and no pastry, coffee and no pastry, 8%, isn't it? 8%.
Yep.
Yes?
No, 8. You said 8.
Coffee and no pastry. Coffee and no pastry, 8. Yeah. Now let's calculate the totals here. So this one would be 20%. This one here would be 80%. And total is 100%, which makes sense, of course. This one here is 76%. And this one here is 24%. And the total again makes 100. Now, let's have some more questions. So let's say I have G here. Let's say I ask for the probability that they had tea for breakfast, given that you know they had a pastry. So this, you remember we did stuff like this yesterday. We know they had a pastry, so we're only selecting from the people who had pastries. What's the probability they had tea? Now, if you look here, it's kind of difficult to get that information from the tree, but it's much easier to get that from the table. So if we're only selecting from people who had pastries, how many people had pastries? 76% of them had pastries. And of the pastry eaters, how many of them were tea drinkers? 4%. So it's 4 over 76 then, which is 1 over 19, which is about 5%, roughly. Okay, so can you see how sometimes questions are easier to answer in one form and sometimes in another form? I think for the tables it makes it very clear to see what the calculation is for this. Try this one. What's the probability that they drink coffee given that they didn't have a pastry? Try this one. What is it?
32%.
Yeah, so the non-pastry people, there's 24% of them, and the coffee drinkers is 8%, so this comes out at 33% then. You get that? Now, if this came up as a question in the exam, you really don't want to be drawing this table if you have the tree. Because often what happens in the exam is they ask you to draw the tree, and then you have to calculate from the tree. And you realise, you don't want to make a table as well. So what we'll do next is we'll look at how we did this to try and figure out a rule without having to draw the table. So let me just delete this too for a moment. So let's imagine I don't want to draw the table, I want to try and use the tree. We try and figure out a formula here. What number did I put on the bottom here?
24.
Yeah, now how did you get the 24? They are the non-pastry eaters. So this is the non-pastry people on the bottom. Now what number did you have on the top? What was it? It was 8. Yeah, now how did you get the 8? These are the coffee drinkers and the non-pastry eaters there. So now we don't actually need the table because we can get these two things from the table here. Coffee and non-pastry. Which part is that? Coffee and non-pastry. That's this one, isn't it?
No, 0.1.
Yeah, it's coffee and non-pastry this way, which we worked out earlier. Where was it? Coffee and non-pastry. There it is there. And then on the bottom, non-pastry. So that would be, let's see, I'll put in red this way, and up here, this way here. So if you don't want to draw the table, and you can draw the table if you prefer to draw the table, but if you don't want to draw the table, we've just worked out a rule to do this probability calculation. Probability of A given B is the probability of A and B, or intersection, all over probability of B. Now if you're not happy with that, that's okay. You can do it using the table, and we'll come back to this in semester 2. We're just kind of having a first look at it here. This is a very, very, very important rule in biology statistics, and I'm going to do a couple of examples now. I'll do the first 4 questions in the book here as examples, but number 4 being really, really important biology example. Okay, so let's do a couple of examples in the book. If you want, you can open them up. I'm just going to do 1, 2, 3, and 4, but I can switch between the two here. Can I scroll down?
Sorry?
Yeah.
The last thing you wrote, I'm sorry, what was that again? The last thing, where is A and B?
B and probability of B, A and B over B.
Yeah.
Yeah. This is the formula we've worked out for A given B.
Oh.
Yeah. Yeah. Okay. So let's have a look at the questions here. Guys, let's have a look. A fair coin is flipped and then a fair die is rolled. Draw the probability tree and calculate the probability of getting a heads and then an even number. So your choices are a fair coin is flipped, and you can get heads or tails, and then you roll a die, and two things can happen here. You can get an even number or an odd number, even number or an odd number. What's the probability of getting a heads? 0.5, and here 0.5. If you roll a die, get an even number. 0.5 is 3 over 6, and here 0.5. So all of this is 0.5. And my question was, what's the probability of getting heads and an even number? Well, there's only one way to do that, this way. So 0.5 times 0.5, which is 0.25. Right, so that's our first example, if you want to write that down, and then we'll do number 2. Yep. Can I scroll down to number 2?
No.
Yep. Number 2. So I'll switch back to it here. You're playing a game in a fun fair. You pick a card at random from a deck of cards. It's either an ace, a royal, or a number card. So what I mean by that is you've got, well, just in case people aren't clear with the vocabulary, you've got an ace, and then you've got the number cards, which will be, I'll switch back now, 2 to 10, and then you've got Jack, Queen, and King then. Yeah, so I just called them in the question an ace, a number card, or a royal card. Yeah. Okay, so let's go back to the question here. So if you get the ace, you win a prize. So you win here. If well, no, I'm just putting a tick here. I'll flick back to it. If you get an ace, you win a prize. If you get a royal card, you flip a coin, and you win the prize if it lands on heads. And then if it's a number card, then you lose. So I'll switch back now. Yeah. So as I was saying, ace means you automatically win. Number card means you automatically lose. And then if you get a royal card, you flip a coin, and you win if you get heads, and then you lose if you get tails. So here we have 3 paths. You can get an ace, number card, or a royal. If you get the ace, then you automatically go on to win. So let me just put in here win and lose, but you know that this is going to be 0. Here, this is win and lose, win. Royal card.
Heads.
You flip a coin then, yeah. So we go. Heads or tails. Yeah, so it's win or lose. You win if you get the heads, and you lose if you get tails. So let's just put in the easy ones first. If you get an ace, you automatically win. So that's a 1 and a 0 here. If you get a number card, you automatically lose. So that's a 0 and a 1. And if you get a royal card, you've got a 50-50 chance. You have to flip a coin. So now it's 0.5 and 0.5. How many aces in a deck? 4 over 52. How many number cards? 36 over 52. And royal cards? 12 over 52. Yeah? 52 cards in a deck. It's cultural knowledge. I don't know if everybody plays cards everywhere. It's not. This is universal. Everybody plays cards everywhere. Okay.
They play Uno.
Sorry, just to be clear, when I say deck of cards here, I don't mean Pokemon cards, Yu-Gi-Oh cards, or any other cards like that. A regular old-fashioned deck of cards. Yes? What? Or a Digimon. Just covering my bases. Hey guys, if you don't, using decks of cards are common in probability questions, so no. Using decks of cards are common in probability questions, so if you didn't know it, a deck has 52 cards, and they're broken into 4 different suits of 13 each. No. Well, do you know what? I think they would give it to you in the exam. What I'm saying is, in this exam, because it's for international students, they would give you the information. But if you were doing an exam for, say, Charles or Maastricht or whatever, or even a probability exam next year at university, I doubt that they would give it to you in the question. So it's broken up into 4 suits. What are they? Hearts, diamonds, spades, and clubs. And then each of the 13 is broken up into ace, and then the numbers 2 to 10, and then you have a jack, a queen, and a king then. Yes. Picture cards, yeah. We'll take this out of the deck. There's 2 of them there. Jokers are sometimes used. Just so you know, if you were ever doing a probability question with cards, like next year or whatever, assume the jokers are not in the deck unless they tell you to. Okay, so can you calculate then probability then of a win for this game?
No winning on card game. We just lose them.
True. Calculate how bad of a chance you have. 4/52 times 1 plus 36/52 times 0. No chance of winning here. And then plus 12/52 times a half. Okay. 0 point. So 19% chance then. Okay, can I scroll down? Yeah. In number 3, listen. In number 3, the question is the same as number 2. I say, you're playing the same game in number 2, but with one change. If you get a number card, you roll a die, and you only win if you get a 6. So the only change is here. That's the only change. The 0.5 gets changed to, so if you roll a die, what's 1/6, yeah. So in my calculation, I just have to change this to 1/6. And can you recalculate? Just go back and change that to 1/6 then. What? Huh? Roll a die.
Because the probability does not get affected. It's the number card. It's just a number card.
Oh, I thought I changed it if you wrote a number card. Oh, so it's 2 changes to it then. I said 1 change. Alright. So we'll have to put it on. Oh, so then we have to redraw the tree. Alright. I'm going to skip this one. I thought it was just a small change. I'll leave this one for you to try. It's nearly the same. It's just these 2 branches here change, okay? This one now becomes a 1/6 and 5/6. And you know what? I'll just do it here, yeah. So instead of 0, it's just going to, that's what you're saying, it's just going to be 1/6. Okay, so what do you get now in number 3 if you change that to 1/6? Can you type it in, please? 4/52 plus 36/52 times 1/6 plus 12/52 times 1/2. What did you get? 31% instead. So your chances go up significantly with adding in the die after you get a number card. Okay, so let's have a look at number 4 now. Oh, actually, there's a B part here in number 3. So the B part is, assuming that you won, what's the probability that you won because you roll a dice? So what would that be? Probability of winning.
If roll. If dice.
Yeah, well, not if dice. Which letter here? If number.
And number, yeah.
But you have it the wrong way around, because I was asking what is the probability you won because you rolled a dice. So you know that you won, and the question is what's the probability that you got a number card, basically, that you ended up going this way. Yeah, so it's probability of number card and winning over probability of winning then. Yeah. Okay, so on the top, what's the probability of number and winning? 36 over 52 times 1 over 6, and then probability of a win. Yeah, but that's when I didn't have to. Oh, that's at 31%. All right. Oh, well then it's that then. 36 over 52 times 1 over 6. Divided by, what you get? 37%. So if you won, then there was a 37% chance you won because you rolled a die. Yeah. Alright, like I said, number 4 is a very important one we'll have to look at. Can I scroll down? And there's some useful terminology in this question that you might want to write down. So, suppose a drug test is 99% sensitive and 99% specific. I don't know if anybody's ever seen those terms before in biology. So, what do you think I might mean if I say the drug test is 99% sensitive?
Very accurate.
Yeah, but what is 99% representing? 99% chance of what? Of what though? Okay, so these are terms you don't know, okay? So, when you talk about the test sensitivity, in this case it's 99%. What you're saying is, the probability that the test result will be positive, given that the person takes drugs, is 99%. This is what sensitive means. It means the probability of a positive test result given that they take drugs. So, if the person takes drugs and they take the test, there's a 99% chance that it will show positive test results for presence of drugs in the system. Specific is the probability that the test will show negative given that the person does not use drugs, and this is 99%. So if somebody doesn't use drugs and they take the test, they have a 99% chance that the test will say negative. So these are the terms sensitive and specific for a test. These are new terms, yeah? But trust me, when you go on to study science or medicine or whatever, it'd be very, very common terms, because as you know, doing tests is a big part of medicine, but of course you also need to talk about how accurate the test is. So this is how we talk about how accurate the test is. We talk about the test sensitivity and how specific it is. 99 is high, yeah, but it's not accurate. We don't use this word. The problem with accurate is because it's not clear what you're saying is accurate. Are you saying that the test is accurate when the person has the drug, or when they doesn't have the drug, or if the result is positive, or if it's negative? Accurate is not clear here. Yeah? Okay, so are we okay with those terms? Yeah? So if we go back to the... Yeah? Yeah, so imagine you have somebody who doesn't take drugs, and they take the test. The test should say they have drugs or they don't have drugs. They don't have drugs. No, but the test, you see, this is real life. No test would say 0. If the person didn't take drugs, it's not guaranteed the test will say they didn't take drugs. There's a small chance of test failure. So in real life, you never see these at 0 or 100. Never. So 99% is really good. It's really high. Do we understand these two concepts on the board? Yeah? Yeah? Okay. So if I switch back to the question. So suppose a drug test is 99% sensitive and 99% specific. That is, the test will produce a 99% true positive. So we also call this a true positive, meaning if they have the disease, the test shows positive, as it should. And we also call this a true negative, meaning if they don't use drugs, then the test shows that they don't use drugs. That's a true negative. What do you think a false positive would be? A false positive.
One.
You got it exactly opposite, yeah. False positive is if they don't use drugs, but the test result is positive. And then a false negative is when they use drugs, the test result is negative then. Okay? And also, we have here that 0.5% of people are drug users as well. Okay? So, what probability would that be? What should I put in here? 0.5%, yeah. But what should I put in the brackets here? Probability of what am I saying? Drug. Yeah. You're saying 0.5% are drug users. So if you take somebody at random, what's the probability that they're a drug user? 0.5%. 0.5%. Okay, so my first question which I want you to do is to draw the probability tree. And before you draw it, you should think about what makes more sense. If first you should do drug user, non-drug user, positive, negative, or maybe you should do positive test result, negative test result, drug user, non-drug user, drug user, non-drug user. I know it's the same, but it's easier to think about it one way than the other. So first draw the tree and try to put in the numbers. That's the first thing to do. Yeah, go ahead, Jack. Okay, let's put in the numbers. So what did we decide on?
Drugs and
Drug or positive first?
drugs.
I'm sorry, I think D first, because
Drugs and non-drugs.
it makes more sense to think about the order as first they're either a drug or non-drug user, and then secondly a test is done. So we have drug and non-drug users, a positive test result, a negative test result, a positive and a negative. Okay, so let's start filling in probabilities here. This one will be 0.005, and this one will be 0.995.
Why did you write?
Oh, okay.
This is 0.5%.
Okay.
Remember, 1% is 0.01. Yeah, that's fine too. That's fine too. You wanted left as percentages? Okay, if that makes you feel better. So 0.5% and 99.5%. Yep. Okay. Now we need to calculate a bit further here. So this one here,
Yeah.
what would it be? This one here would be
99.
99%, and this one here would be 1%. And the non-drug users, 99% for a negative, and then 1% here. Oh, by the way, in this question here, I made both of these 99, but of course they don't have to be the same. In fact, in real life they are often different, because the way the tests are, it means perhaps it's easier to detect a positive than perhaps it is negative. So I think often in real life this could be something like 99%. It's very easy to detect if drugs are present, but maybe this could only be 90%. It's a little bit more difficult to detect if a drug is absent. Okay, so now we have the tree. We can answer a rather important question if you think about it. You have a person in front of you who just took the test, and the test result was positive. Does that mean they're a drug user or a non-drug user? So the first instinct is, well, if the test is positive, there's a drug user. But you remember that we can have false positives. So really the question is this: given that the test result was a positive, what's the probability they're a drug user? That's really the question you're asking yourself. So we have a formula for calculating this. What would it be? Probability of a drug user and positive test result all over probability of positive test results. Now the top one is easy to calculate. It's D and positive, so it'll be this number times this number, so 0.5 times 99%. Now, what's the probability of getting a positive result? 0.5 multiplied by 99 plus, very good, 99.5 multiplied by 1. Right, so calculate this. And before you calculate it, should this number be high or low? What do you think? You think if the test result is positive, you think it should be high. Well, let's see what you get. Calculate it. What number did you get? 33% about. Now just appreciate what you're saying there. What you're saying is a person has just taken the drug test. They have gotten a positive result. The probability that they're a drug user is only 33%. Now this is completely opposite of what your instinct would be, because you would think positive test result means that it's highly likely that they are. Yeah. Now, I want you to have a look at what we did in the calculation and try to identify which part of the calculation is making this number so small. Because 99% sensitive and 99% specific, you can't really do much better than that. It's impossible to have 100%. So what I want you to think about for a minute is, what part of this problem is making this number so small? Yes. Yeah. Or rather, how many drug users are there? Yeah. If you look here, this number is quite small. Really, really small here. And you notice that it's down, where is it here? It's here. And it's here. Now let's just make it a little bit bigger. Let's say instead of 0.5% were drug users, let's say 10% of people were drug users. So if I change that number to 10, what has my percentage become? Let's calculate it. %. Yeah. Huh? Say again? This to 10? Oh yeah, sorry, that 99.5, so this one would become a 90, wouldn't it? Yeah. Can we just change that as well? This one is now a 90. So what do we get? I still think it'll be even higher. Yeah, what do we get now? 92%. Now tell me, wasn't that more the type of number you were expecting? A high percentage like this one, 92%. Yeah. This is very, very important in biology. You can see that even though the test is highly sensitive and highly specific, because the actual number of people with the drug is quite low, it means having a positive test result doesn't guarantee that the person actually has the drug in their system. Yeah. Now there are some famous examples in biology of this. So an example that you might read about next year when you're doing stuff like this, I think HIV and AIDS test would be a good example of this, because when HIV first became a global problem, although the tests were highly sensitive and specific, because at the time the population that was infected was quite low, it meant having a positive test result didn't actually mean necessarily that the person was infected. So that would be a classic example in biology of this type of problem. In other words, it's actually important to know how much of the population could be infected, because it changes what you get here.
So your sample stage matters a lot.
Population matters a lot, how many were infected. Yeah, and you know, there's lots of examples like this in biology with testing. So you can see, basically, if the population is less than 1% infected, I would have serious reservations about using this test. If only less than 1% were infected. You really want more than 1% before this number becomes meaningful. What would it be at 1%, by the way?
34.
Is it much better? At 1%? So that'd be it'd be 99 over 99 plus 99, is it? 50% chance. Still not more than 50%. So at 2% at least, less than 2%, the test is really worthless. Yeah. These are all stuff you'll be looking at next year too, when you do stuff like this. Okay, so what we'll do... Huh? Probability, yeah. This is exactly, the reason I put this question in here is because it's exactly the type of question you would do in medicine. Okay. And also you know that when you do genetics there's probability calculations in it as well, so you can use the probability trees. That's because the ones you do are very, very simple. Yeah, very, very simple. Okay, so what I'll do now is I'll give you this practice exam. You can start working on it, or you can start working on this, but I would recommend looking at the exam. There is a probability tree question in the exam if you wanted to do that one first, for example. And then don't forget to bring these papers with you for the next class as well. So you can start working on these for a few minutes.